Okay, so it's a real pleasure to start the new colloquium series of the spring semester with our guest, Professor Martin Pessah from the Niels Bohr International Academy, the University of Copenhagen. So Martin is someone who works on a very broad range of fields, from astrophysical fluid dynamics in the most general sense and applications to accretion disks, for protoplanetary disks and planet formation, and for accretion disks around compact objects. And recently has also got involved into research for gravitational wave astronomy. He has done a very engaging career since his PhD, which was in Arizona in 2007 at the University of Arizona. Then he moves afterwards as a postdoc to the prestigious Institute of Advanced Studies in Princeton, where he stayed for 3 years. And then after that, he was offered an assistant professorship in Copenhagen, when he moved to Denmark and start from scratch physics in Copenhagen, and especially at the Niels Bohr International Academy. That's what he did. So essentially built really the theoretical astrophysics group, and is currently, well, since a few years, the deputy director, is was a professor. And yeah, I think today, yes, we were talking about what could be the topic for the colloquium. He said, well, I would like to talk about planets this time. And I said, that's good. So, and the choice was his choice. So he's going to talk about planet migration in dark protoplanetary disks.
All right. Thank you so much, Lucio, for your introduction. I have to say that this is my first time in Zurich. I really hope it's not the last one, because I'm having a terrific time, enjoying talking to people and seeing the place. So I really hope I'm gonna have the opportunity to come back sometime in the future. So today I'm gonna talk about work that started really in 2018, and it was really with the vision and I would say deep understanding of dynamics of dust and gas in protoplanetary disk by Pablo Benítez Lambay, who actually thought that dust would actually play a potential role in planet migration. Okay, most people thought that he was a bit crazy, perhaps including myself at the beginning, but we slowly got convinced that this may be a very important process, and this is what I'm going to discuss today. So the second part of the talk is more recent work that we started with collaborators Octavio Aguilera and Marcelo Bertolami, and we are still working on this problem. So I think in the future you're going to see more papers on this. So I did my homework and I asked who was going to be in the audience. I think it's always good to know who you're talking to. And Lucio told me they are numericists and theorists, but no observers. Nevertheless, in order to motivate a talk, it's always good to remember what is that we're after. And I know you must have seen versions of these plots many times. I just want to make one point here. So this is showing the distribution of exoplanetary systems as we know as of maybe a year ago. And then there is a lot of information here. I just want to make one point. There is a large fraction of the planets that we know today within an astronomical unit, the distance from the Earth to the Sun, and they span a very broad range of properties. We have planets that more massive than the Earth, rocky planets, but then we also have icy giants, which have giant planets that have a solid core with some icy or gaseous mantle. And one of the key questions today is how we form these planets. I'm not going to bother about the rest of the planets. We are maybe many more over there, but this is the one that we see, and we better have an idea to explain how they actually came to be and they formed there. And the reason this is a challenge is because the moment you start forming a rocky core in a gaseous disk, as I'm going to explain in detail, these tend to migrate inwards towards the star fairly quickly. So the idea that we have today is that somehow this rocky core forms, and they hover enough time in the disk to accrete significant mass via gas and ices, and they form these giants. But I'm going to explain in the beginning of the talk why it's not such a simple problem, and what is the issue with the simple ideas that we have. So I would argue that understanding this is one of the central problems in planet formation today. And just a second point that I want to do, and this is my last observational slide, is that today we know from ALMA that dust in protoplanetary disks is everywhere. Okay, not only that, from observation, this is millimeter radiation from emitted by dust. There are very large scale structures that we want to understand. But the basic point I want to make here is that if we are to understand, I'm sorry, I keep doing this, getting used to the remote. If we want to understand what is going on, it is necessary to understand the coupled dynamics between dust and gas. And I want to make the point that every single idea that we have to understand how planets form involve dust on one level or the other. However, for reasons I think I can explain in a bit more time, nobody until recently has tried to understand what is the role of dust in planetary migration, which is a problem that we don't know how to solve. So their talk is about this. I'm sorry about this, I just got my finger in the wrong button. So I'm gonna go over some things that you may be familiar with, but even if some things are obvious, bear with me for a moment because I think I'm gonna talk about things that perhaps you didn't have the chance to think about before. So the moment you introduce a planet in a gaseous disk, something very interesting happens. The disk is partially supported by pressure, so it rotates in a sub-Keplerian way, but the planet mostly wants to rotate in a Keplerian fashion. The result of this interaction is that there are certain perturbations exactly in certain locations in the disk, the so-called linear resonances. The details are not important, but because the disk is a gaseous environment, it can sustain waves. These waves propagate and they interfere constructively in certain locations in the disk. And the result of that is this spiral density wave that you see here. And very generically, the situation is such that this wave pulls back from the planet, and this one pulls forward in such a way that this one is a little bit stronger and exerts a negative torque, okay? So this is a core of the problem with planetary migration. So the physics of this has to do with the global dynamics of the disk, and very generically, things move inwards, okay? Now, not all of the torques that are exerted on a planet in a disk have to do with waves. So to talk about this, let me remind you of something that you must have seen before. If you took a course on celestial dynamics or celestial mechanics, and it's the following. This is generically a star, this is a planet, this is in the co-rotating system of the planet. And then this is essentially a solution to the restricted gravity problem, where you actually have a test particle that is a bit farther away from the planet, so it's rotating a little bit slower. So in this co-rotating frame, this particle is going to approach the planet like this. When it gets very close, it interacts with the planet. Remember, angular momentum goes outwards, so there is a negative torque exerted by the planet. So the particle loses a little bit of angular momentum, but now rotates faster. Yes, because angular frequency increases outwards. So because it rotates faster than the planet, in this frame, it would execute an orbit like this, and then it will encounter the planet from the back, and then the reverse process takes place, and then the particle goes out, and then keeps executing its orbit. Absent dissipation, this process will go on forever. This is a test particle now, okay? So this means that there is an exchange of angular momentum between test particle and planet, but on average, nobody neither gains or loses angular momentum, okay? So these orbits are symmetric. So under these circumstances, there is no net torque on the planet by the test particle. So let me summarize what I just said now, is that the classical sources of a gaseous torque on a planet are the so-called Lindblad torque that I just mentioned. This is usually negative. There's a small asymmetry, but it's strong enough to make planets move inwards pretty fast. And now the other source of the torque that has to do with gas is a so-called co-orbital torque. A moment ago, I told you about what a test particle does. But gas behaves differently than a test particle. It's partially supported by pressure. And the dynamics is such that there is a slight asymmetry in these horseshoe orbits for the gas in such a way that the particle feels a slightly positive torque, okay? And the torques that are exerted by the gas in the co-orbital region are quite sensitive to thermodynamics. So there are things that you can do to tweak this. So it would also either give you a more positive torque or a negative torque. But understand that assumptions, this torque is positive. The thing is that this in magnitude is a bit larger than this one, and quite generically, planets move inwards. This is the big problem in planet migration today, okay? So the question is, what about dust? As I said, dust is important for almost every process you can think of having to do with planet formation. It's not a lot of mass that there is in the dust. It's roughly 1%, which is inherited from the interstellar medium. And then I think this is perhaps the reason for which this problem was not looked into detail for a very long time. Thinking that just 1% of the mass, then why would it matter? But the key point, which I think I'm gonna convince you during the talk, is that the dynamics of dust when it's coupled with the gas in this environment is very different than your naive expectation, okay? And I'm gonna set the bar high for myself. I'm not just going to show you results. I want to convince you and explain why this makes sense, okay? So I'm gonna use a little bit of your patience and attention, but let's think about what happens with the dust and what kind of torque it can exert in the presence of gas. So let me build slowly. This is in the absence of gas. I already told you what happens if I grab a test particle. It's gonna execute an orbit like that, the horseshoe orbit. This is gonna appear a couple of times. This is in Cartesian coordinates. If you unfold this into polar coordinates, that orbit looks like that. So the particle comes this way and then comes this way. This is periodic. And then, as I said before, absent dissipation, this is symmetric. There is no net torque on the planet, okay? This, the time that it takes for a particle to execute this orbit is called the libration time. And how long that takes depends on the width of this region. And the width of that region depends on how massive the planet is. That's for a test particle. Now, for gas, I'm not going to demonstrate this, but it's not difficult to understand that particles of gas can also execute this orbit. And there are different regimes in which I'm not going to enter into the details, but intuitively, if the mass of the planet is very, very small, you expect pressure, the gas pressure, to play some role. When the planet is massive enough, then this is not so important, and you have two different regimes. So the scales are different. Now, the last piece of physics that I need before I put everything together is to now think about what happens with the dust particle in the presence of gas, okay? Because essentially the dust particle wants to move in a Keplerian way, but the gas is sub-Keplerian. The particle constantly sees a headwind. This results in a loss of momentum of the particle, which in this context translates into a loss of angular momentum. And quite generically, this particle is going to drift radially inwards. And it does so pretty fast. How fast it does depends on a few things. In particular, it depends on how big the particle is. And again, without showing equations, appealing to your intuition, if the test particle is tiny, 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 then it has to be very well coupled to the gas. And therefore, it's not going to drift with respect to the gas. This is the regime here. Okay, so this is a relative velocity between gas and dust. For tiny, tiny, tiny particles, the speed is 0. And for particles that are very big or very massive, then you do not expect that particle to care about gas. And then you are in this regime. The drift speed, relative drift velocity is 0. But there is a sweet spot, which is parameter. You can use as a parameter this so-called Stokes number, which is just a dimensionless quantity that depends on the size of the particle. There is a sweet spot where this particle drifts with respect to the gas the fastest. Okay? And of course, there's a timescale associated with this. So I'm going to put all of the things I told you before together. And the bottom line is that for a dust particle in the presence of gas, there are two very important timescales. One is the time that it takes the dust particle to librate around the planet. And the other one is the time that it takes that dust particle to drift across this horseshoe region, okay? I can show you the equations. The details are not super important, but the point I want to make is the following. There are two important parameters in this problem. One is the mass of the planet, and the one is essentially the Stokes number of the particle that we're thinking about. You can actually use equations, which are not difficult to derive, but I'm not going into the details. If you set the drift timescale equal to the libration timescale, that gives you this black curve here, okay? Anything underneath is such that a particle will want to drift faster across the horseshoe orbit than it can librate. So essentially, if you want to think about this, a particle comes in, wants to interact with the planet, and instead of executing one orbit, it drifts inwards, okay? That, not for every particle, but there is a region of parameter space where this happens. And therefore, I am not demonstrating this, but I would argue, I hopefully just convince you that it's a interesting region of parameter space, this one underneath the black curve, in which in principle, we expect the orbits of the dust, the horseshoe orbits, to be strongly modified. Yes, they can just not go around the planet, they just need to drift inwards. So this is not a demonstration. Now I'm going to show you results, but I hopefully convince you that at the very least, I'm arguing that this is going to be an interesting region of parameter space, and therefore, this is where we should focus our attention.
Okay.
Yes?
A little bit fast. So let me see if I understood correctly. So when the dust particle is really small, then it moves together with the gas.
Yes.
So that the relative velocity is zero.
Yes.
But then this dust particle is relatively big, then again, which is the regime where it moves together with the gas with the relative velocity. Why is that the case?
No, my argument is,
So if you go back to the
Yeah.
slide. Yes. So we see two different regime in the size, particle size.
Yes.
Where relative velocity is zero.
yes,
So if the dust particle is small, then it's it's basically embedded in the gas and rotate together.
okay, sorry, okay, yes, the point is, sorry, this is a radial velocity, it's just not the drift speed. The radial velocity, if the couples with it's equal the boulder in a gaseous environment, right? And it doesn't go exactly identical to zero, but it gets far less, right?
So it's a radial velocity.
Yes. Here, if you want to think out for the sake of the argument, we can think of an implicit disk. So in principle, the particle is big enough, like a small boulder, then it will not, we just want to rotate in a Keplerian way, so it's not drifting. Okay. Thank you for the question. Okay. So I know this is an audience full of people that are very excellent numericists, so I couldn't avoid telling you a little bit about the numerical tool that we use. I will not do justice to all the power that this code Fargo 3D developed by Pablo Lambay and some collaborators has. But let me show you the equations that we actually are solving for this problem. I will not hide that there are assumptions and restrictions that are set in place to solve this problem, but I would argue that this is the first thing that you want to do to understand the basis of physics in the problem, and then we can build in complexity, okay? So these are the equations of motions for gas and dust in a two-dimensional setting. That sigma is a surface density, and then the equations for continuity look identical for the two of them, and the equation for momentum looks slightly different. Both gas and dust care about the gravitational potential of the star and the planet. The gas will care about the pressure gradient, and there is some term that has to do with viscous transfer of angular momentum. And the key term connecting the dynamics of the gas with the dust is this drag force, which is non-zero when the two speeds are different. And what I want to draw your attention here is that if I had written so this term, which is the drag, depends linearly proportional on the dust density. So in the momentum equation, there was a dust density here, there was a dust density here, which we divided, and therefore this term does really not care about the dust density. But this one that originally had the gas density, the dust density, when we divide by the gas density, has this ratio of dust to gas mass, okay? So the argument is that if this term is small enough, so if I have much more gas than dust, in principle, to a first approximation, I can neglect it, okay? This is not always a good approximation, but as a starting point, and because I said already that the distribution of dust is such that order 1% of the mass is in the dust, I would argue as a starting point is not a bad assumption. Now, the key thing is that this is the only term in these equations that actually has that information. So if I neglect that, the dynamics of this system of equations is insensitive to that mass ratio, but it does care about the Stokes number. Okay? Yes.
So you're not including any effects, any forces in the dust, like rockets?
No, that's a very good point. No. As I said, the reason I was showing the equations explicitly is for you to see what is the problem we're actually solving. All of the complexity that goes into this, and there are other effects that may be important, can be built in. Yes, I will be as explicit as I can out the assumptions, but if there is something that I go over a bit fast or don't mention, please tell me. Okay, the point that I want to make is that even though the dynamics are insensitive to the value of the dust to gas mass ratio provided is very small, that once that dynamics is established, then the torque exerted on the planet is, of course, proportional to the mass of the dust. Yes, because the torque actually has the mass as a prefactor. But the dynamics per se in this regime are insensitive to this epsilon parameter. So for the finiteness, I show you what was the setup that we used when we solved this problem a few years ago. Now the code has grown in a much more sophisticated way. We used a version of the code that was able to evolve gas and dust dynamics. At the time, you could only evolve one dust species. Now the code can handle multiple dust species. It also has MHD, we didn't use for this problem. But I encourage you to go to the Git repository if you want to know more of this code, because everything is publicly available. And the reason to show this plot is just to show you that with the tools that we have, were pretty careful in trying to resolve as best as we could the local dynamics close to the planet. Okay, and this can also be refined. But the initial conditions that we worry about before we put a planet is a two-dimensional disk made of gas and dust. For this, you can derive analytical equations for the steady state. And then we put the planet there. There will be a transient, but the system goes very quickly into steady state. So just to show you one example of how the results look like, if I remember correctly, it was order and Earth mass planet and Stokes number of order 0.1 or something like this. The data is not important, and I will show you the result for other parameters very soon. But generically speaking, you see traces of what I told you before. If you put the planet there, this is the gas. This is a spiral density wave that I mentioned before. And what you notice here is that now the dust here, this black color in the dust distribution, that is, is a void of dust. Okay? And this is what is happening because in this regime, dust particles want to drift fast with respect to the vibration time. There is an asymmetry, which in this case is such that this is seen as a planet as an enhancement of dust, if you want, in the front, and you can understand why this is a positive torque. Now, we may have gotten lucky. This is just one situation in which the results look like what I anticipated. So instead of publishing a paper, I mean, we did publish a paper on this, but instead of just putting this result and claiming that we have something interesting to say, we ran this for 200 combinations. Well, let me just before I jump to show you those results. This is just gas and dust. In order to save space, so to speak, I'm going to overlay the dust on the gas. Okay, so this is showing everything together. This is an inner spiral wave that pulls forward to the planet. This one is the one that pulls back. This one is usually stronger than if it were only up to the gas. The planet would feel a negative torque and move inwards. But here I overlay the dynamics of the dust, which you can appreciate how different it is from the gas dynamics. And in this case, it's such that here there is less dust than here. So this is perceived by the planet as an enhancement of dust. In the front, that's a positive torque. And quite generically, in the region of parameter space I already discussed, this torque can be stronger than the one by the gas. So this is the part where I was going to say. We did this for 200 combinations of Stokes numbers and planets of the mass. And a visual summary of that outcome looks like this. So this is going from small Stokes numbers to larger Stokes numbers, and this is going from small mass of the planets to larger. And I just want to guide your attention to the following. Here it's very difficult to perceive that something very interesting happening, but this is a regime where the dust particles are very well coupled to the gas. And essentially what you see here is the same dynamics that you will see for the gas also happens for the dust. As you increase the Stokes number, then you can see that this asymmetry starts to grow to a relatively big fraction of azimuth. And then as for those values for the Stokes number, as you go up, then that, let's call it hole, starts to become bigger and bigger. Okay? And this is not surprising. What is happening here is that things are drifting very, very fast. And there is a regime here higher up in which you almost have a gap in the dust. Now, if you have a gap in the dust, that distribution is no longer asymmetric, and therefore this mechanism would shut down naturally. Okay. Now, these are values of the mass of the planet in which the gas, of course, perceives the presence of the planet. So if it were only up to the gas here, this planet would be moving inwards. That's the standard result from planet for what is called so-called planet migration of type 1.
Sorry, Martin.
Yes. Yes.
So it's very, very nice, but I have some difficulties to understand certain things. So first of all, in principle, the dust to gas ratio would also change as a radial distance because you would have different, condensation.
Yes.
And this is something that you completely ignore, right?
No, I can be more specific. So this is written there in the approach. So what we do, the fiducial model that we use for this is a standard alpha disk, where the density of the gas decreases with 1/r squared, and then the dust density goes in the same way. Yes. Remember, I'm attacking this problem from, if you want.
I understand. But I'm just saying in reality,
Yes.
as you go further out, you will have lower temperature, so you
Yes.
can condense more. So maybe your dust to gas ratio will increase.
Yes, all of that can be considered.
Yeah.
What I'm doing now, if you want to think about this, is finding the eigenvectors of this problem, understand what quantities are important, and then, those more refined models that you are thinking about is something that we're working these days.
And my second point was that you see that you get something more interesting or more significant as you go to the higher masses. But then I would say that actually, if I have more massive objects, it's less likely that I have a gas that I have dust, because I had to form these planets in the first place. So where would this dust come from? I mean, wouldn't I use the heavies to create the planets, right?
In principle, I agree with you. What we are doing here is, consider the effects of the dust, which has always been, the same point that you are making is valid when people do gas dynamics. So here, the planets put by hand with a small mass, yes, and I can show you in a moment what happens when the planets of the mass starts growing.
No, but I mean, I agree, but
Yes.
I still think that there is a fundamental difference, because if you try to tell me, look, you have to think about the dust in the
Yes.
gas, because it might have some kind of different coupling what is typically assumed, and I tell you, okay, that's very interesting, but I don't think that when I have planets already forming, I would have a large fraction of dust in the disk.
But here, the
in the
fraction of gas is still 1%.
But that's stellar. That's like stellar. I mean, then how do I form the cores? How did I form the planets? Don't I have to take this dust and create tables, planetesimals, whatever you like, in order to form a planet in the first place? So naively speaking, I would say that in the region that I have a planet, the gas, I mean, I should have.
But in principle, I can take this to very early stages where the dust, it is okay to assume that the dust components are the 1%, and then start growing something very, very small.
I understand, but then I don't think you should have a planet. That's my point. I mean, I'm not, anyway, we can continue. But
Yes.
I'm just saying, for me, from a planet formation perspective, if you have 1% in the dust, it's not very likely to have a planet. So it's something.
Okay, as I will show you, we understand how the problem scales with the dust component, and then instead of taking it up, as I will show you, we can take it down and see if we still see the interesting effect.
Yeah,
Okay,
Yeah.
so but let me emphasize this because it's a very important point. Instead of trying to start varying parameters like crazy and including physics, which is not very well understood in their own right, what we did was to take the simplest possible problem that you can consider,
And see what-
which is the alpha disk, and then build on that. My point was at the time when I argued with my colleagues that this was a way that needed to be done, because what we have done will never change. Nobody's going to now alter the standard model for accretion disk that is continued to be used. And therefore, with the basic ingredients that everybody else uses for understanding planet formation, absent dust, we are including dust dynamics. Okay? And complexity can be certainly built, but the problem is that when you start doing that without understanding what were the the basic parameters driving the problem, you are lost. Okay? But I appreciate the point.
Also, your effect will probably be stronger than what you said, right? Because you go to very high masses, then you have the gap dust. So the torque component from the dust will become weak when you open the gap.
The torque component for what?
From the dust. Once you open.
Yes, that's what I mentioned here, right?
So the best cases are probably, they're not the very large ones, right? They're probably the ones in.
There is a suite, of course,
Yeah.
but yeah.
But which is good, I think, because that's usually where you have.
I don't know if this is bad or good. It is what it is with this model. That's my perspective, okay? But what I do want to mention is that at these masses, you are not opening a gap in the gas yet. And that makes sense because the gas is directly affected by pressure support, and therefore it is easier to open a gap in the dust. Okay. So, but this, I hope you appreciate that actually goes together with the arguments that I gave before that were, I think, very, basic physics arguments. Now, full disclosure, and this is where I thought, you can attack me, more strongly. We did assume things that we know are going to break down. For example, here we keep the orbit of the planet to be circular. It's not clear that it's going to be, always forever like this. We keep it fixed to reach steady state, which is only 50 or 60 orbits. So I would argue that that is fine. But preventing the planet from drifting may be a problem because if the planet starts migrating, fast or comparable to this drift speed, then things break down. Okay, I will be the first one to acknowledge, all of these problems, and I actually have a slide with all of the caveats. But again, my point stands. This allow me to think out the physics problem with the questions we are solving, and then we can build complexity. Another issue is that, as I showed you a moment ago, the stock number depends on, for example, the size of the particle, which in principle can evolve over time. That can be built in complexity, and my colleagues have the tools to do this. More importantly, when a dust particle, even if it doesn't change its size, moves through the disk, because the gas density does matter, that is also going to evolve. So in principle, all of this complexity as a function of position and time can be added. But again, my argument is that if you don't understand the basic physics in this simple problem, it is hopeless to understand the results of the more complicated problem. All right. Okay, so what I wanted to say is that this, at the moment is very nice figure, but not so super useful yet. So what we did, and this is a sample of 36 simulations, we have 200 of them. In each of these simulations, and I insist all of them reach steady state, which is actually an important point, what we did was to go and using the dust distribution and the gas distribution, measure the torques exerted on the planet. Okay? So we summarize the results in this plot, which I'm going to explain the main features, and this is the following. This is showing for each combination of Stokes number to be taken discrete, but I will come back to a moment in this, and for different values of the mass of the planet, this shows the ratio of the dust torque to the gas torque. Now, if you notice here, there is a modulus, and that is because in every pixel in this map, the gas torque is always negative. That's the standard gas torque. And the dust torque is negative in a few cases that I can go into detail a bit later, but other than the points which are marked with a cross, the dust torque is always positive. Okay, if it were only for the dust, then things would move outwards. Now this is plotting the ratio, and this is a value of 10 stronger for the dust torque than the negative value of the gas torque. So this is moving very, very, very fast outwards. But as you see, even here, the pale blue regions here, that still means that the planet is moving outwards. Okay, and remember the problem we have with planet migration is because of a very slight asymmetry between the inner wake and the outer wake. So a pale blue here means the thing is moving outwards. Okay, no questions asked. Now, before you ask me, but I can tell you more in detail, this square rectangle that you see here, those are high resolution simulations because these look very funny. We were worried about this numerical garbage, but we understand the dynamics in this regime, to a certain extent, to understand enough that if you remember before I told you, for Stokes numbers that were the gas, the horseshoe orbits of the gas had two different regimes. One that was affected by pressure and the gravity of the planet, and the other one only by gravity. So here, where the Stokes number is relatively small for the dust, then the dust does feel that pressure component. So this regime is actually different than this, and I can show you in detail the simulations that are marked here. So the point is that the dynamics taking place here is non-trivial. There is a transition between a pressure-dominated regime and a gravity-dominated regime, which in between can be, subtle changes of the Stokes number give you different values of the torque. But what I'd like you to appreciate, if you squint your eyes a little bit, this shape that I was showing you before is more or less present there. Okay, before I gave you very hand-wavy arguments, some very simple equations, but now this is what I was telling you before. I could have shown you this plot. I hope I convince you that we understand, broadly speaking, why this looks like this. The dynamics here is more complicated, and I can come back to that. But the point that I want to make is that now we essentially have a map of parameter space that, given a fixed Stokes number and a fixed mass of the planet, we understand the ratio of the dust torque to the gas torque. And remember, this is at the fixed location in the disk, which we happen to put at one astronomical unit. We have to choose some fiducial radius. Yes?
So the thing I don't understand, maybe you explained it and missed the understand it is. So why is this gap opening up behind? Is it because it does somehow just collide with the planet, or
It's a three-body problem modified by drag.
Yes.
I can we actually what happens in reality. I have a slide in this as an extra slide. It turns out that when you analyze, we didn't do this analytically, but when we put dust particles behind the planet, that's unstable region. So it actually gets you cannot collect things there. So it's two effects if you want. It's drifting faster than it can vibrate. But on top of that, if you actually put a test particle, it's an unstable region. I have to be honest, we have to decide when we were writing this paper whether we would include all of that understanding in the same paper. We were thinking that we were going to be scooped, so we put this paper out. And that problem of understanding in more detail, this is a good project for a student, understanding in more detail the three-body problem in the presence of drag, that would allow you to understand what is going on in more detail.
yeah, so the thing I'm missing is just that So what makes it the different? What creates the symmetry? So it's not unstable in front of the planet. Is that the point? So you're just saying it's just unstable behind, but not unstable in front.
Well, I think things in the front will end up going to the region in the back and then go out. As I said, I don't have a profound understanding of the dynamics close to the planet, but I guess my job was to convince you with some, I would argue, slightly hand wavy, but based on physics of timescales, and we have the simulations. It is true that to understand actually, I can show you the dynamics of in this regime, and you will see why it's not such a trivial problem to provide an obvious answer. But the best answer I can give you is that this depends on the properties of the dust particle, and we know that this starts to empty out. The asymmetry has to do, I cannot better explanation at the moment, that how the three-body problem behaves when you have this drag.
The other question is, so you showed that when the Stokes number is very large, that means essentially having, sorry, is it like very large particles?
I have to say something,
Yeah.
allow me. In principle, you should be slightly skeptical of Stokes number this big, because then you're, remember, I show you equations, we are simulating the dust as if it were a pressureless fluid. So that approximation has to break down. So that's the reason we stopped there and we didn't continue. Okay,
Yeah,
in principle.
So because it seemed to show that this behavior, the general behavior holds across the different Stokes numbers, and then gets even more pronounced as the Stokes number gets very large. So I wonder whether one could go to the large Stokes number regime to understand why you form this gap, right? So in this regime, you're in it's the case where essentially you have no interaction anymore, right?
Sorry.
Between the gas and the
Let me make sure I didn't misunderstand you or you misunderstood me. The gap in the dust starts opening up here. And I would argue that in order to understand this problem better at the level that you feel more comfortable talking about larger Stokes number, I think you just need to change the approach. Because the fluid approximation, I think, at some point breaks down. And then you will have to solve a problem where you have gas. You may have a dust component, you can measure simulate as a fluid, but then for particles who are really bigger pebbles or boulders, you need to do an N-body treatment with that.
right.
So I also have a follow-up question. So you said that you consider a few orbits, right, for the simulations?
No, what I said was that within 50, 60, 70 orbits, we reach steady state.
Okay.
This is assuming that there is a steady state in which dust and gas is being supplied, right?
And so you account for the fact that basically at different disk locations, I will reach the steady state at different times.
No, I haven't. No, what I said is that this map has been obtained and the 200 simulations were done with the planet fixed at 1 AU. I could have put it at 2 AU, 3 AU, but now the next part of the talk is understanding how to use these results as measured at one given location and to scale that across the disk.
Okay, so this is for one given fixed location.
Yes. And if somebody has a more clever idea how to build the problem from scratch, I'm happy to discuss that. We saw that there was no, of course, you can just try to evolve the full dynamics, but then you run one simulation. We are getting to the stage of doing that to see if this is consistent with that. But the approach here is put the planet fixed, don't let it move, and measure. Okay? All right. So what have we learned so far? That in principle, I hope I convince you with some caveats and approximations that large torques could arise from the dust component. And I think that the key word is that we have not assumed anything peculiar. I'm not saying that dust, like in some other settings where we have to understand that the dust is important when we have, the same mass in gas than dust or, 10 times more. Here, I just assume the standard run of the mill, 0.01 dust to gas mass ratio. And this is not a process that works always for any combination of Stokes numbers and mass of the planet. There is a region of parameter space where this is more relevant, and I show you what that was. But now we want to understand, I think I would argue that in principle, if one went to make the mental experiment of what is going to happen, it's not hard to envision that this dust torque, if it's present, then it's going to alter the migration history and potentially the formation history of the planet. So now again, with the tools that we had and trying to keep ourselves honest with the approximations, we were thinking, what is the simplest way in which we can actually integrate these equations of motion? And again, in principle, you can add as much complexity as you want. You will pay the price because it's going to be expensive. So I would argue is that now we have done the first part, we will be better positioned to do the more complicated stuff later. So now as I said again, we measure everything at one location. We want to have some sort of model that allows us to scale the dust torque as a function of radius. So let me show you a couple of things. So the angular momentum is just this for the planet. The torque is the time derivative of the angular momentum. And the point that I just want to make is pretty simple. This depends on the radial derivative of the position of the planet with respect to time. And therefore, the standard equation for planet migration, that it tells you that the radial speed of the planet is going to be linearly proportional to the torque. Okay. So the point is that every single study, or the very vast majority of them that you have seen studying planetary migration in the context of protoplanetary disk, has set this torque to be the torque exerted only by the gas. And now we have a hint of what the dust component may do. Now, there is no magic. You have to actually think out important quantities. And this is just the most important things that we have to put into place to have some reasonable models to work on this problem. In principle, the torque exerted on the planet, both by the gas and dust component, is going to carry out the global structure of the disk. Remember, now our job is to integrate the equation of motion of the planet across radius. So how the disk looks like, is going to matter. It's also going to matter what is the dust to gas mass ratio. I already argued originally that it was going to be linearly proportional to the dust to gas mass ratio in this case. And then here is where you can also add a lot of complexity. We are going to assume that the Stokes number does not change. That is not realistic, but that can actually be considered a posteriori, because this is going to tell you which regime of Stokes numbers are actually more interesting. And then, in principle, I know there is a lot of work also, in particular in Zurich, to understand how planets grow. Here, we cannot afford to do something very fancy. We are going to make the planets grow by hand. But this is a parameter, because we make them grow slow, we make them go fast, and then we have a hint of how much these are going to affect the problem, okay? All of this can be refined. So before I show you some results, I need to tell you a couple of things. And this is just, I think, my last set of equations. We can rely on the people that have worked on planetary migration of gaseous disks for now a few decades. I then understood that even though the problem is very complicated, if you have, for example, an isothermal disk, then the torque exerted by the gas is some number. For example, this one has to do with the radial density, the gradient of the density of the disk. This number is negative. You put it here. This number is positive. This is minus. This is your negative torque from the standard problem. But the reason I'm showing you this is for you to appreciate that this gaseous torque, what people have shown, is that it's scaled with this quantity, which is called gamma p. Gamma p is not difficult to understand what it is. If I just give you a piece of paper and I ask you, write the, what are the relevant dimensional quantities in this problem, the combination that gives you a torque have to do with the density of the gas, the radius of the planet to the fourth power, and then the angular frequency to the second power, right? This has units of the torque. Those are the scales of the problem. So they naturally appear there. There are two other, quantities that appear here, which are perhaps not easy to guess, but it's not difficult to understand the role. There is a ratio of the mass to the planet to the star that appears there square. This is natural, I would say, because a bigger planet would interact with the disk in a stronger way, and therefore the torque exerted on the planet by those waves is going to be bigger for larger masses. And then if the disk is more puffy, so this is this aspect ratio, so if H is a bit higher, then I think it's natural to expect that the torque is going to pull a little bit less strong way. So the only point that I want to make is that we have now measured things in one radius. We need to scale things to a global setting. And then for the gas component, people have studied for a long time that there is some function that has to do with the thermodynamics of the disk, if you want, times gamma p. Okay? So the disk models can be more complicated. You may have gradients in temperature, density, and some other things. But the point that I want to make is that people have shown that when you only have a gaseous disk, then the Limbian torque that I talked about before and the corrotation torque by the gas can be a complicated function of those gradients. But naturally, the scale of the problem is always the same. So both of these torques, the corrotation torque and the Limbian torque, scale with the same way, with gamma p. Okay, that's natural because those are the dimensions in the problem. But now I'm going to use this to motivate the model that we put together for the global dust torque. Okay, so before I told you that the dust dynamics was insensitive to the dust to gas mass ratio if that was small enough, but I also told you that naturally the torque that cares about the mass of the dust enters in a linear way in the problem. So the dust torque for an arbitrary mass density of the dust, which cannot be too large, okay? But if a value which is different from the fiducial one is going to relate to the fiducial one via this ratio. That's what it means that it's linearly proportional in epsilon. Now, what I'm going to assume, and this can be studied in more detail, but it's a first good approximation, is that the way that the dust torque scales globally is the same way that the gas scales globally, with this factor gamma p. So that says that, for a given dust to gas mass ratio, then if I want to understand at the different position than the fiducial one how the dust torque behaves, that is a ratio of these two gamma p's evaluated to different radii. This may not be correct, but it seems the most sensible thing we can do without doing 10,000 numerical simulations, but it can be tested. In all honesty, we have not done that yet because we're still understanding what the impact of this model is. But now, if I put these two things together, I have this equation. So now the torque exerted by the dust at an arbitrary distance, at an arbitrary but small dust gas mass ratio is linear in the dust to gas mass ratio, is proportional to the ratio, to this ratio that is here, and proportional to the gamma p that I introduced before. And you notice that this quantity here is precisely what we measured before. Before, we set the dust to gas mass ratio to a given number, and we put this on 1 AU. So that's this map here, which is this quantity, and now I can scale that to different dust to gas mass ratios and to different positions in the disk. Yes?
No, because this was just for one position. So now you tell me that this map would be the same for all positions.
No, I'm telling you that it's going to scale with gamma p. So
But this is assuming that this ratio that you got here is that this is a global phenomenon, and
That's what the simulation.
But Martin, can you go back to one slide?
yes,
Yes.
This
So,
one?
Yes, that's right. So for example, if you look at the torque on gas,
if we look at, sorry,
gas torque,
yes,
then it depends not only gamma p, but also it's a complicated some function of density temperature.
yes.
So gamma p scaling is a sensible thing, I believe, for the dust torque. But then what about this free factor? You don't.
No, but that's precisely the assumption that we are making is that the gas torque, sorry, is sensitive to all of these thermodynamics. Yes, but here the assumption is that the way the dust scales with radius, frequency, and the dust and the gas density is given by gamma p. It may not be correct. I argue that is the most sensible one to use, absent a deeper understanding of the entire problem, which can be obtained with numerical simulations.
no, but there is still something, sorry, I didn't get the function that you showed was for fixed radial distance, right?
Yes.
And now you take this function, which is the ratio between them, and you say that, is it okay to assume that also when you take different radial distances in a disk, or are you going to use also only that for a given fixed radius, which is the same as the one from the simulation?
No, I mean, the question starts telling you the answers into the question. So this, we are okay, right, here, with the
Yes.
distance.
And I'm
So
also okay
here-
with two, although it might not be true, I'm fine with that.
Yes, and so this equation is not inertial putting those things together. Right?
Oh, that, yeah. That's.
Okay.
Yes.
It's,
So this is a strong assumption, but I'm telling, yes, okay? Okay, so one thing that we are missing, so to speak, is that we want to integrate the equation of motion for a planet moving in the disk. Now, the masses here, they have been binned. And if I'm going to assume that the mass is accreting somehow while it's moving the disk, that is going to be a pretty bumpy road, right? Because when the moment the mass changes a little bit, then the torque changes in a non-continuous way. We expect nature to be continuous. Do you agree with the statement or not?
No, I don't understand.
So this is, by necessity,
You can extrapolate, right?
yeah, that's my point. So what we did was to do a bilinear interpolation. The reason I was careful with this because I have been asked this question before, and so what we did is just a simple, in that map, a bilinear interpolation. This washes out some details that may be important. In particular, you can see now there is a, that funny region of parameter space that was very delicate. Here it just shows, with red. But I would argue that this is actually a conservative approach because that red region, if anything, is gonna make the planet move inwards, right? So here, artificially, the bilinear interpolation is, decreasing the importance of the dust torque in that region. But the point I want to make with this plot that has been done at 1AU is that, comparing what you would get in this map, the isothermal disk that everybody used with something more refined. So the details of this map, of course, are going to care about the details of the physics of the disk. But the point is that this is a pretty robust outcome of what we're doing, okay? And now this is for a given distance, and this is going back to your question, under the assumption that the ratio scales with gamma p for different distances, now you can do for an isothermal disk and a non-isothermal disk as a function of now distance, okay? What is the ratio of, what is the total torque over gamma p? Okay, so this encodes the radial dependence by assumption. The point that I want to make is that here, for an isothermal disk, absent dust, this is all, slightly negative. This is your, problem with standard type 1 migration. Everywhere in this parameter space, absent dust, or for dust component, which is very, very tiny, which is very well coupled to the gas, then all of this means that the planet is moving inwards. But when you start including at the 1% level, the dust component, now you have these big, blue regions. And remember, pale blue, still the thing is moving out. This, strong blue is running away outwards. Okay, so this is again at a given radius and for a given Stokes number shown there. So the question is, now we can grab a model, put the planet at the given distance, initial distance, with the given initial mass, and by hand, artificially make that mass grow, just to parameterize that. And then that is going to tell you how that, model planet is gonna move in this map, and how it's gonna be torqued either inwards or outwards by the gas and the dust component. Is the exercise clear?
Non-isothermal is adiabatic. Or what you call the non-isothermal disk is
non-isothermal means that this is a refined part of the people that do population synthesis model. You have it's a 1 plus 1D model, so it's a radial model that assumes vertical hydrostatic equilibrium in the vertical direction, and then the structure that you see here is inherited by the structure of opacities in the radial direction of the disk. So I don't want to get hung up in the details of all of those models, because the point to be made here is that if you squint your eyes, the structure of this is not super sensitive. Of course, how the planet is going to move, we'll care about that.
Wait, can I ask, sorry, one more, because I think I'm missing a point. So in the diagram to show this from all the simulations, that was for a fixed radial distance.
Yes.
And I think your argument is that if I account for the dust, you can have a different torque, and then instead of migrating inward, you can also migrate outward. Get it? I agree with that.
Yes.
But now when you do that for this simulation and you change your radial distance and you use these maps, it's based on only this set of simulation that you had for a fixed radial distance.
Yes.
And you're assuming that you can use the same map for all these radial distances.
Yes, and that may not be correct, but it's the best assumption I can make today.
Okay.
And I would argue, actually, I would argue that is the only natural assumption to do, to take before solving the problem fully, which I'm not saying we are not going to do, but we want to understand, get a hint for this.
Okay, but you could just take one square from the entire simulation and just take a different radial distance and see, is it the same way?
Okay, I'm going to answer your question. I think I have a plot, but it's not plot here. I can, in the paper, we do this. So what we did, in parallel with this, we actually assume that the scaling was the one that was not inheriting from gamma p, but from the simulation. But the radial assumption, there is no way out unless you start solving the problem at every single radius.
Okay, sorry, now I got it.
Yes. So if you want, I think perhaps people will think that this is just investing too much time on this, but what we have done with ourselves is to justify that it makes sense to solve this problem much more carefully. Because if this had shown that there was no hope for the dust, then forget it.
Yeah.
But this is telling you there may be something interesting. All right. I like this, the reluctance. I'm the same way. You cannot imagine how much we discuss how to do things when we're working on this. So I think that the exercise, I hope, is clear with the models that we have. I can start with the mass for the planet, small, and then say by hand how fast it's going to accrete, and see how the planet moves in the disk with these smooth bumps. The slide I'm going to show is a little bit busy, but let me guide your eye. These are results that are obtained for 3 different types of disks. So the vanilla flavor alpha disk model, something that I explained is a bit more refined in the thermodynamics, but the map does not change too much. And then this one, again, by hand, because we know that the disk is not there forever, we'll just simply remove with some parameterization, some mass from the disk. This is not how things happen in reality, but just to give us a flavor of what happens when you're removing mass from the disk. And what I want to point your attention is to the fact that these dashed lines in the different panels, that is what you see in the absence of dust. Yes? And if you pay attention, it doesn't matter where you put the planet. It doesn't matter how fast the planet accretes mass from the environment. All of these lines go very fast inwards. This is the problem we are trying to address. So what I hope I have been argued and even fighting against in favor of the assumptions is that the moment you assume that there is a dust component, not with the crazy dust to gas mass ratio, but just 1%, then the dynamics can be strongly modified. And here is not how a real planet is going to evolve, but this shows quite generically, I would say, that very naturally, this is for Stokes number 0.1, but we have done this for other values. Then here you have a case that if the planet is taking too long to accrete, that means that it spends more time in the rational parameter space where the dust torque is positive, so it flies away. If it's growing faster, okay, then it hovers around this location, goes a little bit outwards, and then it goes in. So the point that I want to make in the beginning of my talk, and I appreciate all the questions you asked me, that I just didn't want to show you these results. We have built intuition of why this is behaving this way. The reality may be different, but I would argue that we understand pretty well the physics that we put in, and that has allowed us to understand the physics that we're getting out. This is not often the case too often in astrophysics these days. So this model is fairly simple. This is just for Stokes number 0.1. What we did just to study the sensitivity of the results for other parameters, and you can do this with many other things, is to show how things change with the modest increase in the dust density. And there are a few things to be said here. Here, the dashed lines are no longer the dustless disk, but it's a disk that has 1% by mass of the dust. So this all should be quite similar, but this is for a non-evolving isothermal disk. The point to be made here is that an enhancement of 2 in the dust to gas mass ratio actually gave you pretty different dynamics. And then we did the exercise of doing it 5 times and 10 times. And here you can start worrying about this because, for doing all of this, I said that epsilon was very, very small. And here you might start getting uncomfortable. So if you don't want to reach this result too much, I'm fine with that. I'm also on your side. But it's just to get a flavor of, I guess the point is that, it's quite sensitive to the dust component.
So just try to understand the plot. You have 2 different models, one with the dust, one without the dust, and then you put the planet at 1, 10, and various separations,
Yes.
and then they evolve. Right?
You make it accrete by hand at a fixed rate. And we just parameterize that.
What about the time scale?
The time scale is inherited by the accretion rate, right? Because the accretion rate is assumed to be constant by hand,
Right.
then you can read off, if you actually
the mass increase.
exactly. So again, you can make a far more refined model for mass accretion, but I would argue that the building blocks are in place now. Okay.
Sorry.
Yes.
Why is it? Maybe you could say this in simple words. Why is it that the high get faster?
Yes.
It's more massive and it's still, right?
You're talking about the gas component.
No, I'm talking about this. But I'm still trying to understand what I'm seeing. This is not a time evolution, right? This is,
No, it is.
It is.
But
okay,
no,
so
but
yeah,
it's an
because
important
as
point.
they create, it moves upwards, right?
Yes.
Okay, so, but if I start with a more massive planet, I thought you already said that they're, okay. So what's the effect if your planet mass goes up? Let's say you start from 10 sort of masses, 10 mass.
I already told you the answer. The planet is not going to get out of dust. But if you see this is where we stop actually, right?
Right.
So here is so let me repeat.
So it's just the effect of the plot that you showed before, that this effect of the dust becomes weaker. As
Exactly.
the mass goes up.
That's the
There's
reason.
something else.
No, it's dust. Yeah. So it's It's a limited. So if you want, to be brutal with this, I would say, this has not solved the problem of inward planet migration, and I agree with that because eventually, the standard physics will, take over. But the important point is that for the first time, and somebody can correct me if I'm wrong, you have a very, I would argue, a priori robust mechanism with the physics that should be in place, with the dust that is there, that naturally makes things move outwards. And depending on how fast the things are accreting, they will move outwards, faster and farther away. They can hover around, and they eventually will come back. Then it's up to other people to tell me what are sensible initial conditions to consider, for how small the mass of the planet can be and how far away I can put it.
How does any of this depend on, let's say, the mass of the gas disk or all the other properties, let's say the mass of the host star and stuff? I mean,
Well, yeah, of course.
so
But
this is this setup is for, let's say, the solar system particularly.
this setup is for the standard run-of-the-mill disk that is being assumed to run today every single planet population synthesis model that you have seen.
It's the same model everybody is.
But we can change it, of course. But
I mean, so what's the reason? Because this is assumed to be the model for the for our solar system.
Yes. But all of those things you can, of course, nobody, I think I spoke fast and strongly in some parts. Of course, all of the pieces are talking about entering into the problem. We have to solve the problem of some fiducial values. You can ask me, we have.
To be fair, it's true, but I mean, of course, this is for a very specific set of parameters which are known, right? So of course, people, if they do responsible work, they do change these parameters and they see how the outcome changes. And if you say this is to model the solar system, and you really
I didn't say that.
No, fine, okay. Then you didn't say it, but if you think about planetary systems or exoplanets, and you see that your effect is kind of more interesting at the lower masses, which was your point. Actually, if I can complain, I could also say that, now we know that in this mass range, we typically have planetary systems. So if you put another planet, it will completely change the top.
Yes.
Which will also change your
Yes.
result. So that's
Yes.
another thing that one has to be.
Yes.
Right?
Yes, true. Ideally speaking, what I want to do is to grab some, set of parameters for the disk, put, in principle, several cores at different locations in some random way, include the gas physics, coupled. I want to relax approximation that epsilon is very small, and I want to allow all of the cores to migrate. We can write a great proposal to do this. It's not going to be cheap. Yes, but my point is that I think solving that problem is well motivated now. That's my point. Yes. I never said that I was going to solve every problem in planet formation in this one talk. So the takeaway from this talk, because I think we're running out of time, is that I hope I convince you that from the first time we have actually taken into consideration in some approximate and perhaps crude way the effects of dust in planet migration with no peculiar assumptions. I think that is key. Okay, there are details that can be built on this, and I'm happy to discuss all that. Then I would argue that this is a natural mechanism to make things hover or even move hours, where they can perhaps have more time and go to the regions of the disk where there is more material to be accreted, and eventually those things will migrate in. I'm not saying we have explained all of the hot Jupiters and things like this, but it's a natural mechanism that I think should not be ignored. That's the point. When when people come and give you talks about how important is that for planet formation, ask them if I consider this consistently on how things move in the disk. Okay, I hope we are going to move past that stage. I'm not going to go over detail in this, but you can ask me more questions. You ask me several. This is what we have not considered. It's a long laundry list. I don't know if it's exhaustive, but it's pretty honest. And my summary slide is just one with a couple of figures, just to make the point that for the first time, we have considering gas and dust dynamics in a fairly consistent way, I would say, and quite generically and naturally, we do obtain the deviations from the expected dynamics on a dustless disk. I think that's the takeaway home message. If I convince you of only that point, I'm happy. Thank you.
Thank you very much.
An extremely interesting talk. As you know, we do n-body simulation with planetesimals, and your mass scale stops at 0.1. And we include
My mass, here below, yes, yes.
Negative torque in these simulations, and we typically have a big problem at the beginning of the simulations that everything migrates in, right? And this sets the stage then for further growth of planets in a very large way. So I think this effect is very interesting. We don't include it. If we were to include it, we would have to know what happens at much smaller
Yes,
masses.
yes.
And also, how do we, a fixed Stokes number is probably not what is realistic in a real disk. How does the Stokes number, because of the switch at Stokes number of 0.3, how can we handle that? Or what does it look like?
Well, it's not a switch. It's a transition in regimes, and in which the brutal reality is that in a protoplanetary disk, you're not going to get to choose what is going on. There were several effects happening, and you have the dust evolving in Stokes number, not only because it's drifting radially and moving, but also because it's subject to different disk densities, and also there may be coagulation. There are things that can be complicated at whatever level you want. One point that you're making is very true, which we could address at this level even, that we didn't go too far down in mass. And this is honestly because there were already 200 simulations in 2018. We have modest computational resources, even though Fargo did this very fast. And then we have just to choose the region of parameter space that we know was relevant. If you notice, and I didn't say this explicitly, but here you can see what you're saying. In order to bring this down, actually this was brutally extrapolated. One should do better than this.
Mhm.
But I think if you allow me, from what I said before, for the very small dust component, very small dust, that is going to follow the gas. So that's not going to solve your problems. But I think there's enough circumstantial evidence to argue that even small particles, which are not that well coupled to the gas, may have an important effect for small mass planets. So this is a point that can be studied. Take the masses of planets to be very, very tiny and see how it reacts when you have different dust of different sizes.
That's very, very interesting. I think
I have to be honest, when we started working on this, after the first paper, our collaborators wanted to push strongly forward for doing the kind of point that you are seeing now with grab the run-of-the-mill model that people use today for planet population synthesis and just blast it with this and get the results. We did that. It was impossible to understand what was happening. Now we have a better idea of what is happening because we can switch on and off the growth of the dust, move things around, assume a mixture of gases of that, and then what we learn from here, we can tell why things are moving in or out, or why they are growing slower or not. I have some preliminary results, but not until I don't understand them better and not so open to show them. And this is the talk, but I can talk to you all.
Yes, I was wondering, all of the simulations are purely hydrodynamic, right?
Yes.
So I was wondering, do you think that this would make a difference if you include MHD, especially if you have MHD from the planet? I guess this could influence the migration, right? If you're in the inner part of the disk, you are either this material.
Yes. Yes, the answer is yes. We can not say no, right?
No.
The honest truth.
But what do you think?
The honest truth is that that will happen in the absence of dust, and that's something we also need to consider.
Yeah.
I think there is a huge, I have the focus, on a daily basis with a range of people. There is people who, most refined physics to do it, that they deal with is this because there are a lot of complexity in the data dynamics. And I talk to people who do, full 3D simulations of a protoplanetary disk with Hall and bipolar diffusion and, all of the toys that you want and see a jet from a planet. Yeah, our job is to bring these things together.
So, do you think this affects is also with armor?
That's an excellent question. And the truth is that this, is going to be as long-lived and it takes the planet to grow essentially and cut the gap. So, whether you can, and then we can understand, we need to understand how long even that gap in the dust is, how long-lived that is. So this is a more ephemeral phenomenon, right? Because it's going to last as long as the range of masses in the planet is, from what I showed, order 10 Earth masses.
But sorry, I thought that the gap was only in the dust. Not
Yes,
in the gas.
and this is what he's asking.
Essentially.
So the question is, suppose for 1 second that everything that I say is absolutely correct. Can we observe this? Yeah, this is likely to be not a very long-lived process.
But you could catch, hence it's luck, right?
Yes.
Actually, Judith has two questions, so maybe we can try if you.
What should I do? The chat? If I activate my audio, okay?
Yeah, your laptop audio.
Okay, I know when to start. There are several questions.
Yeah, maybe Judith, you can try to speak and see if we can hear you.
I'm.
Mm,
I,
1 second.
do you hear me? Do you hear me?
Sorry, can you hear me?
I can hear you,
Yeah,
but
go ahead.
okay. So one of my questions was, how do you define a typical non-isothermal disk? Because there is stellar heating, and that depends on the stellar type.
Yes.
There is also requirements on the resolution. For example, if in the planet vicinity, the higher is the resolution, the deeper you go into the gravitational potential well, and therefore you have higher temperatures, and that's going to affect the torques. So I'm not really understanding how you define a non-isothermal disk, just one.
No, I grab a particular model which my collaborators understand that is what people use when you don't have dust. I can happy to tell you all the details have to look at the paper to be completely honest. But the point that I wanted to make by showing those figures was that you can have a relatively more complicated structure for the disk, and then the main features that you observe in the torque maps are not that sensitive to that. They are not going to disappear. That's perhaps the point that I wanted to make.
Okay.
But I agree with you. Of course, depending on the details that you put in the model, you are going to have different migration histories.
Yeah. So okay, thank you. The second question was that since Willy Klei's paper, like I think 15 years ago, he showed that accretion and migration is coming hand in hand since both of them are affected by the torques. So if you preset the planet accretion rate, then aren't you presetting the migration rate also?
Yes, I think I was clear on that. We are setting this by hand and keeping it constant just to have some figure of merit. When the time comes, I have a more consistent model that deals with accretion. I have an idea of, depending how fast or slow that accretion rate is, how that is going to affect the torque. But yeah, I completely agree with you. I hope that I didn't mislead anybody, implying model what I just really said in an open and honest way. Yeah, it's going to, of course, it's going to. Yeah, that was the point of the plot that I showed. If I keep things by hand fixed, then that is going to affect the rate at which not only accretes, but the rate and the way it moves in the disk.
Yeah. Okay.
So
great.
Better models for planet accretion. There is no doubt of that.
Okay. Great. Thank you. And the third question was, what do you think about the Daniel Price type of one dust fluid type of simulations, where he tries to simulate a multiple dust species, but just with one dust fluid?
So my opinion on this, if I have to be blunt, is that it cannot work. And it's a very simple physical argument, because I can set up a disk where the gas components are accreting inwards, and I can choose two different dust species, and depending on the size of those species, because of momentum conservation, I can make one of them move inwards, and I can move the other one maybe outwards by hand. And that is to capture with one dust model. I mean, it may be useful for some things, but I can see several multi-species. We know this. We can do this in a piece of paper. By having a standard disk, and I put a number of species with different mass ranges. Some of them will follow the gas and move inwards, and some of them are going to move outwards. And that you cannot. I have used this argument. The first time how to use this argument was in a paper we wrote on the streaming instability, because people were trying to use these models to consider there were multiple species in streaming instability. And again, the same argument holds. It's momentum conservation what kills you.
Okay, thank you.
Thanks.
One very last quick question. So all these models, like normal models that people do on migration, they assume that this is running.
Yes.
So
Well, yes. You go ahead.
If you had a third, I'm thinking out about the effect of the dust. If you had a turbulent, but the turbulence is not technical. So
yes. If you allow me, I will refine the question a little bit.
Yeah.
Because what you're saying is true. I think people have diffuse boundaries of how they refer about momentum transport, alpha viscosity, and turbulence. Let's remember what alpha viscosity is as an effective model to account for turbulence, but the distance cells are actually laminar. Yes, exactly. So if you were to be consistent and seeing that what is responsible for momentum transport is turbulence, which should also stir up the dust. Sorry, that should be considered. And to first approximation, these features may be, washed out. An argument in favor of saying that this is unlikely to be completely dead is that these are relatively large-scale features, right? So there may be a regime of parameter space in which this is shut down. So this is actually one of the most important reasons to do include magnetic fields, because we know when things get hot enough, things like magnetic rotation stability will be active. That gas is going to be stirred, stirring up the dust, and some of these things may be washed out. Okay. Can I shut down this?